Today's lecture is about the discovery of the atom, or the history of the discovery of the atom, because as you'll see as we progress through this, that the atom has taken a little over 2,000 years to come full circle to what we understand today about the atom. But we need to go back about 2,500 years to the time of the Greeks. There was a famous thinker at the time named Democritus, and as he was sitting around the campfire one day, he imagined a rock, or as you see in this picture, a piece of clay. And he believed, you can cut the clay in half and it's still clay. Well, what if you take that smaller piece of clay and cut it again and continue to cut it and cut it again and again and again? And if you could make fine enough cuts, Democritus believed you would get to a point where you couldn't cut the clay anymore. And that small, indivisible piece of material is what he called the atom, which comes from the Greek word atomos, which means indivisible. Democritus believed everything was made up of these tiny, indivisible particles called atoms. Now that's kind of remarkable because Democritus came up with this idea of invisible particles just sitting around thinking one day. So he's credited with the discovery, or the first idea of the atom. Now, it's purely speculative. He had no way to back up his idea of the atom, even though today we know it's right. He had no way of backing it up at that point. So what happened is one of Democritus's contemporaries named Aristotle, which you probably have heard of, he was the more popular guy at the time. And the popular thought of that day was that everything in nature, all matter, was made up of four basic elements: water, fire, air, and earth, and that making different combinations of these four elements is what made different types of matter. Aristotle did challenge Democritus and asked him a series of questions, and because Democritus couldn't back up or couldn't support his idea of the atom, that idea of the atom kind of was buried, and was buried for almost 2,000 years. And it was this popular belief that all matter is made up of the four basic elements that persevered for a really long time. So even though Democritus was right, he wasn't accepted in his beliefs at the time. Now there's a long history of chemistry between Democritus and the ancient Greeks until modern chemistry. So we kind of skip ahead a great deal in time to a guy by the name of John Dalton. John Dalton was actually began his career as a school teacher. And he was one of the early chemists. And there were three basic laws that he was investigating at the time. As you can see here, he was looking into the law of conservation of matter, the law of definite proportions, and the law of multiple proportions. If you need some background on those are in your textbook at the beginning of chapter 3. This lecture is not going to explain those, but if you have questions, please ask in class tomorrow. But based on these series of experiments, John Dalton came to the conclusion that Democritus was actually right, that all matter is made up of small indivisible particles called atoms. Now the difference between Democritus and Dalton was that Dalton had scientific proof or some scientific data to back up his claims. So almost 2,000 years later, Dalton provided the first scientific proof that atoms exist. As you can see here in the corner, in this bottom corner, this is how Dalton viewed the atom. They were small, solid particles, and each element had different types of particles, which leads us to Dalton's atomic theory. That's summarized here in this cartoon, but it's also summarized in your book. And you can read through these, but the belief that atoms are all indivisible particles that cannot be further divided. They're invisible. We can't see them as individual atoms. Atoms of the same element are identical with each other. Atoms of different elements are different from other elements. And that when elements combine to form compounds, it's because these atoms are acting in a certain way. Now, all of these parts of John Dalton's theory are still accepted today, except for one, and that's this fact right here, that we now know that atoms are not small, solid particles that can't be further subdivided, but rather they have particles within these particles. And that's what the rest of this lecture is about, the discovery of the particles inside of the atom. The first particle that was discovered was the electron. The first subatomic particle that was discovered was called the electron, and this was discovered by a man named J.J. Thomson And he was working with a piece of equipment called the cathode ray tube, or sometimes it's called a Crookes tube. And inside of this tube was a gas. And he had the tube hooked up to some electricity. And when the electricity would flow through the tube, you'd see this glowing beam of light. And Thomson and his colleagues came to the conclusion that that glowing beam of light, or that stream of light, is made up of tiny little particles. Well, that's all and good, all well and good, but they further took this Crookes tube, or this cathode ray tube, and did some additional experiments. And I have a diagram of what they did. Here's the Crookes tube here. And what they found is that that beam of light, that beam of particles, could be bent. And what they found was that that beam of particles would deflect away from things that had a negative charge. And as we all know, things that have opposite charges attract each other, but particles that have similar charges will repel one another. So the conclusion was made that this beam of light inside the cathode ray tube was made up of particles that had a negative charge. And that's how the electron was discovered, based on this work with the cathode ray tube. As you see through here, Thomson did a lot more than just work with this cathode ray tube, but the main contributions that Thomson has is that he discovered that the atom has particles inside of it. And if you look here at the bottom, we call Thomson's model the plum pudding model. He viewed the atom as a solid particle that was solid and diffuse. It has a positive charge all throughout, kind of like a chocolate chip cookie is solid. That's the cookie part. Embedded in this solid positive atom are these negatively charged particles that we call electrons. Now, while Thomson didn't know much about the electrons other than that they had a negative charge, another guy by the name of Millikan did a very historical experiment called the oil drop experiment. And we're going to do an analogy of this experiment in class later this week. And you can read about his experiment a little bit more in detail in the textbook, but essentially what he did was he took a fine atomizer of oil, and what the atomizer does is it sprays out a fine mist of particles. And what he was able to do is alter the charge, the electrical charge between these two electrical plates. And he would change the charge so that he could get a mist, a particle, suspended right in between. And as he did that, he was able to discover the charge of the electron. And that's the important thing here. He discovered the charge of the electron. I'm not interested in you knowing the value of that. So that's not something that you need to commit to memory. But because he was able to discover the charge of the electron, he knew how much mass of oil he had sprayed in. And so using dimensional analysis, he was also able to calculate the mass of the electron. So Millikan just gave us some additional information about the electron, the mass and the charge. Again, you don't need to commit these values to memory. One of my favorite experiments was done by a New Zealander by the name of Ernest Rutherford. And he was working with radioactive materials. And as you guys should recall, radioactive materials are those materials that decay. They break down into simpler elements, and when they do so, they give off radioactive particles. And he was using this box of radioactive materials that he was able to shoot out some positive particles. And you might want to write this down, that those were called alpha particles. And the symbol for alpha particles is that it's a helium. It's a helium atom with a positive charge. But he took this beam of alpha particles here, and he aimed it right at a really thin piece of gold foil. And he believed, based on Thomson's work and what they believed the atom looked like, he believed that those alpha particles with a positive charge would travel all the way through that piece of gold foil. Now, because we can't see atoms or these types of particles, he had to come up with a way to detect them. And that's what you see surrounding this piece of gold foil was this plate. This plate would glow in the exact spot where a positive particle would hit it. Okay, so he's aiming positive particles at this gold foil, and he's got this metal plate behind it that can detect where they hit. Now, what Rutherford expected is that those particles would travel all the way through and he would only see a glowing point right behind the piece of gold foil. That's what he predicted. That's not what he discovered. In fact, Rutherford was really shocked by his discovery. He found that a lot of these particles would get deflected a little bit, and some even more. And because this plate went almost all the way around, he was extremely shocked when the particles would bounce off and come almost directly right back towards him. He said it was as if you took a cannonball and you shot it at a piece of tissue paper, and the cannonball would bounce back and hit you. That's how shocked he was. He had no idea that this would happen. So we have to rework, or Rutherford had to rework how he viewed the atom, because the current view at the time could not explain these results. So here's a different view of what Rutherford believed. Now this view is a side view or a cross section of that gold foil. As you can see, it's only a few atoms of gold thick. It's only a few atoms thick. And so what would happen, because you're shooting positive particles at the atom, when they would deflect, they must be being deflected by something positive. Because as you recall, particles that have similar charges will repel each other. Now, in order to repel these positive particles, that positive charge in the atom had to be condensed down to a very, very, very small place. And so the discovery, in the end, what Rutherford discovered was that all of the positive charges are concentrated in a small area of the atom called the nucleus. Now you have to remember, the nucleus is extremely small compared to the rest of the atom. In fact, the analogy that's always given is, if you view the atom as the size of the Edward Jones Dome or a stadium, then the nucleus is only as big as a marble on the 50-yard line. So it's extremely small. So this diagram does not do it justice. And so the view from Rutherford is all those positive charges are in this tiny space, and the electrons with the negative charge are somewhere outside of the nucleus. A better view might be this one. That here's the nucleus. Again, it's much larger than it actually should be in the diagram. All the positive charges inside of the nucleus, and the electrons are out here somewhere. The atom, according to Rutherford, is mostly empty. It's mostly empty space. Now that's very different than Thomson's view. He viewed the atom as solid. It was all positive, it was diffuse, but it was solid. So Rutherford is the first one to suggest that there's empty space inside of the atom. Now we know a little bit more about the nucleus now. In fact, if we look here, this is greatly enlarged size of the nucleus, so it's very drastically wrong. But we see those positive charges, those protons, so we call those protons now. But we also have these other particles inside of there, and we now know that those are called neutrons. They have a neutral charge. They were discovered by Chadwick, and again, dates are not important, but the neutron was discovered to be located inside of the nucleus, and those neutrons play a part in the stability of the nucleus. Because think of this, if you have all of these positive charges compacted down into a tiny, tiny place, positive charges should be trying to repel each other. And they are trying to repel each other. So there's got to be a really strong force inside of the nucleus holding those particles together, causing them to not repel away from each other. And so what's doing that is, along with the nucleus, we have these really super strong nuclear forces that are keeping that nucleus stable. And if we went on and talked about nuclear chemistry, we would be disrupting those nuclear forces. And if we could break open this nucleus, we've got a lot of energy that's waiting to be released in there. But that's another topic for another time. So for this particular talk, we have talked about the discovery of the atom up until modern chemistry. Now, the view here of this atom is not how we currently view the atom, but that's the where we stop in terms of today's lecture. We stop with Rutherford and Chadwick. So as of now, we've got a nucleus with protons and neutrons in the middle, and we have electrons somewhere outside of the nucleus with a negative charge. The atom is mostly empty space. Next time we chat, or next time I'm chatting at you, we'll talk a little bit more about what we can do with the idea of protons, neutrons, electrons, where they're located, what their charges are, and how that relates to information that we find on the periodic table.